Okay, as I was saying before the video cut off there, since Meg is moving at 70 miles per hour and John is moving at 60 miles per hour and they're moving towards each other, they effectively have 130 mile per hour relative speed, and if they travel for 1 hour before they meet, that means that they were separated initially by the 130 miles per hour. That's another way to get this answer besides the way that I did it here. Okay, so then let's move on, and in the second part of Part B, if you can read that, let me try and zoom in just a little bit. Whoops. Says, how long has John driven when the two pass each other for the second time? So this is where I'm going to make heavy use of the diagram that I've got drawn here in Part A. I already know that T1, where they first meet, is 1 hour. So then I'm going to find sequentially what the distance between T1 and T2 is. I mean, the distance in the time direction, so the time difference between T1 and T2, and then between T2 and T3 in stages, and that'll simplify the getting to the final answer. So let me grab another sheet of paper. I'll do it here. I'm going to try and keep my drawing in frame so that we can use that as we calculate. There we go. Okay. Now, I need to find the difference T2, the difference between T2 and T1. So what I know is that in the time T2 minus T1, traveling still at her original 70 mile per hour speed, Meg here, this is, again, this one is Meg and this is John. Meg is traveling at 70 miles an hour, and in the time, in the extra time after the original 1 hour that she continues traveling, she accomplishes an 80-mile distance. Okay, that's what the question tells us. So, simply solving here, we can find, let me grab my calculator. Let's see how I can get this in frame. Okay, 80 divided by 70 is 1.14 hours. So T2 minus T1 equals 1.14 hours. When I looked at the solutions that everyone had, I tended to see a lot of people saying that T2 itself is 1.14 hours, forgetting that there's a whole hour of travel that happens before this 80 miles gets covered. So really T2 here is equal to this 1.14 plus T1, which is 1 hour. So in other words, going back to my original drawing, I can label this now. T2 equals 2.14 hours. Okay? And next, finally, I need to find what T3 is. So let's see. In order to do that, I need to write an equation for Meg's position and John's position as a function of time, noting that now the equation has changed. I can no longer use the ones that I used originally because Meg changed directions. Right? Now, actually, I can use the same equation for John's motion because his motion never changes. Right? He never changes direction. So the position of John as a function of time is still what I had before, d, which we've already found to be 130, I'll just leave it d right now, minus 60t, where t is, we're starting from, counting from 0. Now, let's work with Meg. I first need to know where she is at time t2, what position she's at, in order to calculate, in order to write an equation for her motion. So let's see, x meg, position of meg. I know that in the first hour, whoops, going back to the original drawing, in the first hour, since she traveled at 70 miles an hour, she would have covered 70 miles, clearly. And then in the second, from T1 to T2, the question had told me that she traveled 80 miles before she decided to turn around after passing him the first time. So therefore, the position that she reaches at this point is going to be 80 plus 70, or 150 miles. So she starts, quote unquote, starts from the point of view of the motion that we're going to consider after T2. So this equation I'm going to write down is only valid for, let me specify, for t greater than T2. She's starting at that position, and then she's moving in the negative direction with a speed of, says here, if I go back to the question, she's going to drive now at 80 miles per hour in the reverse direction until she catches up. So it's minus 80 t, but I have to be careful. It's not actually t that I want here, because I now need to start counting the amount of time after she turns around. So the time after T2. So I need, excuse me, in this equation for her position, I should write t minus T2. Okay, which is known because I've already found T2. All right, so I've got my two equations. Now if I want to find the time when they actually pass, I'm going to set those positions equal to each other, just like I did before for the first time they passed. X John equals X Meg, which means that D minus 60t is equal to 150 minus 80 times the quantity t minus T2. Guess that got cut off. We won't. I'll scroll away from my drawing for a second here. Okay, I'm going to plug in the numbers that I know, those being 130 for the distance minus 60t equals 150 minus, I can distribute this is 80t minus, and now I'll plug in, sorry, this is a plus because I've distributed this minus sign and this minus sign cancels. Anyway, 80 times T2, which I found earlier, you recall, going back, I've labeled it here in my drawing, T2 equals 2.14 hours. So 80 times 2.14. I'm going to collect all my similar variables, so add 80t to both sides. 20t is equal to 20. That's subtracting 130 from both sides, plus 80 times 2.14. And now I'll grab my handy calculator, do some quick math. I'm going to take 20 plus 80 times 2.14 and divide that by 20 to get 9.56. So T equals 9.56 hours. Now that's the time starting from the beginning, how long till they eventually meet. And what does the question ask? The question again asks, how long has John driven when the two pass each other for the second time? So that answer is the 9.56. Okay, great. I'm going to stop the video now, and we'll go on to week 3 in the next one.